informed on, well, some pretty big topics.
That's right.
And today, we're going really deep. We're looking at something incredibly fundamental, a sort of beautifully choreographed dance that happens everywhere. It's behind starlight, it's behind the tech, in your phone.
It really is everywhere. We're diving into the cosmic dance of light and matter, specifically why photons and electrons seem like such, well, perfectly matched partners.
Exactly. We're going to try and unpack this really essential relationship between light and matter.
And our mission for you listening is to pull out the key insights from our sources. Think of it as getting you quickly up to speed on a cornerstone of how reality actually works.
We'll be looking at the dancers themselves, the quantized electron, the quantized photon, and the big rule they always follow: conservation of energy.
And understanding this interaction, it really opens up everything. How atoms hold together, how we see, even how things like lasers and solar panels work.
Okay, so let's start with one of the dancers.
Yeah.
The electron. I think, most of us probably picture this tiny little ball orbiting a nucleus, like a mini solar system.
Right, the Bohr model picture. And it was useful, but, well, our sources make it really clear that's just not the whole story. It's a massive oversimplification, actually.
So what is the electron then, according to quantum mechanics? It gets weird, right?
It does get weird. The electron has this amazing dual identity. Sometimes it acts like a particle, a localized little thing, but other times, crucially, when it's bound in an atom, it behaves like a wave.
A wave,
okay.
Right? How does being a wave inside an atom change things? Does that, force it into specific spots?
That's exactly it. Its wave nature is paramount when it's confined. Think of a guitar string.
Okay.
A guitar string is fixed at both ends, right? So it can only vibrate in specific ways, specific patterns, standing waves that fit perfectly between those fixed points. You get the fundamental note, the harmonic.
I can't just have any random wiggle.
Precisely. And the electron's wave, confined by the pull of the nucleus, is similar. It has to form a stable standing wave around the nucleus.
So the wave has to fit into the orbit.
Yes. Only orbits where a whole number, an integer number, of its wavelengths fit perfectly around the circumference are allowed. If it doesn't fit, the wave interferes with itself destructively and, well, that state just can't exist.
So this isn't just some mathematical rule someone made up. It's a physical consequence of the electron being away.
Exactly. It naturally explains quantization. Niels Bohr, back in 1913, he had to just postulate that angular momentum was quantized to make his model work, but the wave nature derives it. It's the why.
And that directly leads to quantized energy levels.
Yes, because the electron's energy is tied to its wave properties. So if only certain wave patterns are allowed, only certain energies are allowed. It's like steps on a staircase.
You can be on step 1 or step 2, but not hovering in between.
Precisely. Discrete energy levels. And it's important to remember these steps aren't evenly spaced. They generally get closer together the further you get from the nucleus.
And this solves that old classical problem too, doesn't it? Why atoms are stable.
Oh, absolutely. Classically, an orbiting electron should radiate energy and spiral into the nucleus in like a fraction of a second. The universe shouldn't exist.
Right. Bit of a problem.
A huge problem. But quantum mechanics says there's a lowest possible energy level, the ground state, N1. An electron there cannot lose any more energy by radiation because there's no lower allowed state to fall into.
So it's stable. It can't spiral in. Phew.
Exactly. That inherent stability, thanks to the ground state, is fundamental to, well, everything existing, matter itself.
And when it is in a higher level?
That's what we call an excited state, and that's when it's ready to dance with a photon.
Okay, so that's our first answer, the electron, this confined wave with discrete energy steps. Now, what about its partner, the photon, light? Our sources say its story starts with a kind of crisis, the ultraviolet catastrophe.
Yeah, that was a big puzzle at the end of the 19th century. Classical physics predicted that hot objects should radiate infinite energy at high frequencies in the ultraviolet, which they obviously don't.
Thankfully.
Right. So Max Planck in 1900 was trying to find a formula that matched experiments for this black body radiation. He found one, but to make it work mathematically, he had to assume energy wasn't continuous. He proposed it was emitted in discrete chunks, or quanta.
But he thought it was just a math thing, not really real.
Initially, yes. He called it an act of desperation, just a mathematical tool.
Enter Einstein, 1905, his miracle year.
Exactly. Einstein took Planck's idea and ran with it. He used it to explain the photoelectric effect, that thing where light shining on metal can knock electrons out.
And the weird part there was, a dim blue light worked, but a super bright red light didn't.
Precisely. If light were just a continuous wave, brightness, intensity should be all that matters. But it wasn't. The color, the frequency, was critical. A dim blue light, high frequency, could eject electrons. A very bright red light, low frequency, couldn't, no matter how bright.
Which makes no sense for a wave.
None at all.
Yeah.
Einstein realized the only explanation was if light itself is made of discrete particles, photons, and each photon carries a specific amount of energy determined by its frequency.
The famous E equals hf, Planck's constant times frequency.
That's the one. E.A. Feller. It means the energy comes in packets. To knock an electron out, a single photon needs enough energy, needs high enough frequency, to overcome the electron's binding energy. It's a one photon, one electron interaction.
All or nothing.
All or nothing. A photon can't give part of its energy. This indivisible nature is absolutely key to the whole dance.
And does this E.A. Feller connect to Einstein's other big equation, EMC22? Does a photon have mass?
Well, it has zero rest mass. But because it has energy, and energy and mass are equivalent, you can think of it as having an effective mass. Lower mutable is HFC22R2. It carries momentum.
So it can push things, like a tiny billiard ball.
Exactly. And that particle-like momentum becomes really obvious in higher energy interactions.
Okay, so we have our quantized electron, our quantized photon.
Ah.
But this dance isn't random. There's a strict rule, right? Conservation of energy.
The bedrock principle. Energy can change forms, but the total amount always stays the same. It's never created or destroyed.
And there's a deeper reason for that, isn't there? Something about time.
Yeah, that's Noether's theorem. Emmy Noether showed this profound connection. Symmetries in nature correspond to conservation laws. The fact that the laws of physics don't change over time, time translation invariance, directly leads to the conservation of energy. It's beautiful, really.
Even in the quantum world, energy is conserved. I know things get a bit fuzzy there.
Well, on average, for an isolated system, energy is precisely conserved. Now, the interpretation of quantum measurement gets tricky. You have things like the Copenhagen interpretation with wave function collapse, which looks like a sudden change, versus many worlds where energy is conserved across all branches.
Okay, maybe let's not dive down that rabbit hole today.
Probably wise. But the key point is, for any completed interaction between a photon and an electron, energy conservation holds perfectly. And this brings us back to the perfect match.
Lock and key.
Exactly. The electron have these discrete energy levels, that's the lock. The photon arrives with a discrete amount of energy, E8. That's the key. For an interaction like absorption or emission to happen, the photon's energy must precisely match the difference between two electron energy levels.
It has to be the right key for that specific lock.
Precisely. An atom can only emit or absorb photons of very specific frequencies corresponding to its allowed energy jumps.
What about the Heisenberg uncertainty principle? Doesn't that let energy be borrowed for short times?
Ugh, that's a common misunderstanding. The principle, delta E at delta C gec, doesn't mean energy conservation is violated. It relates the uncertainty in a state's energy to its lifetime, delta T. An excited state isn't perfectly stable, it only lasts for a tiny time, maybe 10 seconds.
Okay.
This finite lifetime means its energy isn't perfectly sharp. There's a tiny inherent uncertainty or blur, delta E. This translates into a slight spread in the frequency of the photon it emits. It's not borrowing energy, it's defining the natural line width or tempo of the emission.
Got it. So it's more about the fuzziness inherent in short-lived states.
Exactly.
All right, dancers introduced, rules established. Let's talk about the actual steps, the choreography. How do photons and electrons actually interact?
The most fundamental steps are absorption and emission. They're essentially mirror images.
And responsible for those fingerprints of elements.
Absolutely. In absorption, a photon comes in. If its energy exactly matches an allowed energy jump for an electron, the photon gets completely absorbed, it vanishes, and the electron jumps to that higher energy level, an excited state.
All or nothing again, if the energy is slightly off.
Nothing happens. The photon just passes by. This is why, if you shine white light through a cool gas, you see dark lines in the spectrum. Photons of specific frequencies have been absorbed, removed by the atoms.
And emission.
That's the reverse. An electron in a higher, unstable, excited state naturally wants to fall back down to a lower energy level. To do that, it has to shed the energy difference. And it does that by creating and emitting a photon whose energy perfectly matches that energy gap.
Creating the bright lines you see in an emission spectrum, like a neon sign.
Exactly like a neon sign. Each element has its unique set of energy levels, so it emits its own unique set of colors, its barcode.
Now, Einstein apparently saw two types of emission.
Yes, this is crucial. First, there's spontaneous emission. This is what happens naturally. An excited atom, after some average lifetime, just randomly spits out a photon in a random direction with a random phase. That's the source of most light we see: starlight, candle flames.
Okay, the normal kind. What's the other?
Stimulated emission. This is wild. If a photon comes along and its energy exactly matches the energy the excited electron wants to drop, that incoming photon can trigger or stimulate the electron to fall down and emit its photon sooner.
Okay, so it speeds it up.
It does, but here's the amazing part. The new photon that's emitted is a perfect clone of the incoming photon. Same energy, same frequency, same direction, and perfectly in phase coherent.
Whoa. So one photon goes in, two identical photons come out.
Precisely. One becomes two, two become four. You get amplification. This is the principle behind the laser light amplification by stimulated emission of radiation.
Clever. Harnessing a quantum quirk.
Absolutely. Our sources also mention electrons don't always fall in one go. They can cascade down through intermediate levels, emitting multiple lower energy photons that add up to the original absorbed energy.
Or they can lose energy without emitting light at all.
Right, especially in solids. They can transfer energy as vibrations to the material lattice, basically, as heat. That's called thermalization or non-radiative decay.
So the dance gets more complex depending on the photon's energy, right? It's not always just simple absorption or emission.
Definitely. Energy is the choreographer. At very low energies, like visible light interacting with small molecules, you get coherent or Rayleigh scattering.
That's the blue sky one.
That's the one. The photon essentially bounces off the whole atom or molecule without losing energy. It's elastic. Blue light gets scattered more effectively than red light by the nitrogen and oxygen in the air, so the sky looks blue.
Amazing. Okay, what happens as the energy goes up?
We move into the realm of X-rays and gamma rays. At low to medium X-ray energies, say 10 to 100 keV, the photoelectric effect becomes really important. Here, the photon doesn't just nudge the atom. It hits hard enough to transfer all its energy to a tightly bound inner shell electron.
And knocks it right out.
Knocks it right out of the atom ionization. The photon vanishes. The electron flies off with kinetic energy equal to the photon's energy minus how tightly it was bound. This effect is much stronger in materials with high atomic numbers, like calcium and bone or lead shielding.
Which is why bones show up on an X-ray. They absorb more photoelectrically.
Exactly. But as the photon energy climbs higher, say hundreds of keV up to many MeV, Compton scattering starts to dominate, especially in materials like water or soft tissue.
How is that different?
Here, the photon interacts more like it's hitting a single, loosely bound outer shell electron. It's like a billiard ball collision. The photon transfers part of its energy to the electron, knocking it out, and the photon itself scatters off in a different direction with less energy, meaning a longer wavelength.
So photoelectric is total absorption. Compton is partial energy transfer and scattering.
You got it. Photoelectric depends strongly on the material, atomic number Z. Compton depends more on just how many electrons are there, electron density.
So a clear shift in behavior as energy increases. Wave-like scattering, then full absorption, then particle-like collisions.
Precisely. The photon reviews its dual nature depending on the energy of the interaction.
But it gets even more extreme, doesn't it? At the highest energies, the dance becomes truly transformative. EMC22 territory.
Oh yeah. Now we're talking about creating matter from light. If a photon has energy above 1.022 MeV, that's mega electron volts, and it passes close to an atomic nucleus.
Wait, 1.022 MeV. Why that specific number?
That's the exact amount of energy equivalent to the rest mass of an electron plus the rest mass of its antimatter counterpart, the positron, according to EMC2.
Oh, okay. So what happens?
The photon vanishes. And in its place, poof, an electron-positron pair appears out of pure energy. It's called pair production. The nearby nucleus is needed to sort of soak up some momentum and allow the conservation laws to work.
Creating matter and antimatter from light. Wow.
And then, typically, that newly created positron doesn't last long. It finds an electron nearby, and they annihilate each other.
Turning back into energy.
Exactly. Their mass converts back into energy, usually producing 2 gamma-ray photons, each with 0.511 MeV energy, flying off in opposite directions.
A complete cycle. Energy to matter, antimatter, and back to energy.
A perfect demonstration of EMC222.
Is there anything even higher energy?
Yes. At very high energies, typically above 10 MeV. A photon can have enough energy to bypass the electrons entirely and smack directly into the atomic nucleus.
Into the nucleus itself.
Yep. It can knock out a neutron or a proton or even an alpha particle. This is called photodisintegration. It actually changes the element transmutation. It takes enormous energy to overcome the strong nuclear force holding the nucleus together.
So the photon goes from a gentle messenger to an electron ejector to a matter creator to a nucleus breaker.
That's a great summary. Its role completely changes based purely on its energy, revealing this profound duality.
Okay, so this dance isn't just happening in labs or theory books. It's happening out there in the universe and right here in our technology.
Absolutely. Let's look at the cosmic scale first. The light from stars. That's the result of trillions upon trillions of these photon-electron interactions happening constantly in the incredibly hot, dense plasma of the star's core and outer layers.
Just a chaotic storm of interactions.
Pretty much. But when you average over all those countless random quantum emissions, you get a smooth, continuous spectrum out. That's blackbody radiation. And remarkably, its shape depends only on the object's temperature.
Not what it's made of?
Nope, just temperature. And there are laws describing it. Wien's law tells you the peak wavelength, hotter stars peak at shorter, bluer wavelengths. Cooler stars peak at redder wavelengths.
So you can tell a star's temperature just by its color.
Essentially, yes. And the Stefan-Boltzmann law tells you the total energy radiated. It goes as temperature to the fourth power. So if you double the temperature, it radiates 2 honor to 4 joules, or 16 times more energy per unit area.
Powerful tools for astronomers.
Incredibly powerful. And the cosmic microwave background radiation, the afterglow of the Big Bang, is the most perfect black body spectrum ever observed. It's like a baby picture of the universe telling us its temperature back then.
But the universe also has these extreme environments, right? Producing incredibly high energy photons.
Oh, yes. Very high energy, or VHE, gamma rays. We're talking energies 100 billion to 100 trillion times higher than visible light. These are messengers from the most powerful particle accelerators in the cosmos.
Like what?
Things like the regions around supermassive black holes, active galactic nuclei, or AGN, also massive star explosions, supernovae and gamma ray bursts, even some binary star systems where there's a neutron star or black hole.
How do they make such energetic photons?
Usually involves electrons accelerated to almost the speed of light. They might spiral in magnetic fields, producing synchrotron radiation, or these super-fast electrons can collide with lower energy photons like starlight or the CMB and boost them to gamma ray energies. That's inverse Compton scattering.
Can we detect these VHE gamma rays directly?
Not from the ground. Our atmosphere absorbs them. But when a VHE gamma ray hits the upper atmosphere, it triggers a cascade, a shower of secondary particles.
An air shower.
Exactly. These particles are moving so fast they actually emit a faint flash of blue light called Cherenkov radiation. Telescopes on the ground detect this faint flash, and by analyzing the pattern, astronomers can reconstruct the energy and direction of the original gamma ray. It's quite indirect, but very effective.
So nature uses this dance on a grand, sometimes chaotic scale. But we figured out how to control it, haven't we? Build our own little ballrooms.
We certainly have. Spectroscopy is a perfect example. We're just reading those atomic barcodes we talked about earlier.
Shining light through a sample and seeing what gets absorbed, or heating a sample and seeing what gets emitted.
Precisely. By measuring the exact wavelengths, we can tell exactly what elements or even molecules are present and how much. Think about environmental testing, checking for heavy metals in water, or food safety analysis, or forensic science. It all relies on those unique spectral fingerprints from electron energy level transitions.
And lasers. You mentioned stimulated emission. How do we make that happen reliably?
The trick is to create a population inversion. Normally, most atoms are in the ground state. In a laser medium could be a gas, a crystal, a semiconductor. You pump energy in to deliberately put more atoms into a specific excited state than are left in the lower state.
Flip the normal situation upside down.
Exactly. Then you put this medium between two mirrors, forming an optical cavity. A few photons get emitted spontaneously. They bounce back and forth. And because of the population inversion, they trigger stimulated emission much more often than they get absorbed.
Amplification kicks in.
Amplification kicks in, and because stimulated emission produces identical coherent photons, you get this intense, single-color, highly directional beam of light. It's an amazing feat of controlling quantum mechanics.
And then there are semiconductors, the heart of all our electronics.
Absolutely central. They rely entirely on controlling how electrons and photons interact within specific materials.
Like in an LED, a light-emitting diode.
Yeah. In an LED, you use materials where electrons can exist in certain energy bands. You apply a voltage, pushing electrons into a higher energy band and creating holes, absences of electrons, which act like positive charges in a lower band. Where these bands meet, at a p-n junction, electrons fall into the holes,
Recombining,
and when they fall, they release that energy difference as a photon. The size of the energy gap in the specific semiconductor material determines the energy and therefore the color of the photon emitted. Red, green, blue LEDs, different materials, different band gaps.
So electricity in, light out, and solar panels are the reverse.
Pretty much the exact opposite process, photovoltaics. Sunlight, made of photons, hits the semiconductor material, usually silicon. If a photon has enough energy again, think photoelectric effect, it knocks an electron out of its place, creating an electron in a hole.
Creates charge carriers.
Right. And the solar cell has a built-in electric field, usually from another p-n junction, that immediately separates these electrons in holes, pushing them in opposite directions.
So they can't just recombine right away.
Exactly. This separation creates a voltage across the cell. If you connect an external circuit, those separated electrons flow through the circuit, creating an electric current.
Direct conversion of light into electricity. No moving parts, no noise.
Silent, clean, direct conversion. It really highlights this fascinating duality, doesn't it? Nature often produces these incredibly energetic but chaotic high-entropy interactions, like the inside of a star spitting out random black-body radiation.
Whereas our technology often aims for the opposite.
Yes, we impose order. We create low-entropy, highly controlled, coherent processes like the beam from a laser, or the efficient, directed flow of charge in a solar cell. Same fundamental dance, but choreographed differently.
So wrapping this up, it really feels like the photon-electron relationship isn't just important, it's foundational. A perfect, necessary partnership.
It really is. It's dictated by quantum mechanics, governed by energy conservation. That lock-and-key mechanism, the electron's discrete levels, and the photon's discrete energy packet makes their interaction precise and fundamental.
And we've seen how the dance itself changes so dramatically with energy, from just scattering information around to ejecting electrons to actually creating matter or breaking nuclei.
An incredible range of choreography.
And it drives everything from the largest cosmic events, stars burning, galaxies glowing, high-energy jets down to the technology we rely on every single day, lasers, computers, solar power.
The same fundamental rules underpin both the universe's chaos and our engineered order.
Ultimately, the photon is the messenger, isn't it? Carrying this quantum record of its interaction with an electron, sometimes across billions of light years.
It's the primary way we know anything about the universe, really. From the smallest atomic scales to the largest cosmic distances, it's photons interacting with electrons that bring us the information.
Which leads to a final thought, maybe. This dance isn't just fundamental to how reality is, it's also fundamental to our ability to see it, to measure it, and maybe, just maybe, to understand it.